Here is question 6 from tutorial 6. So we have a sequence here, an equals n factorial divided by n to the n, and we need to verify that the ratio of two consecutive terms is given by this equation, and then we need to use the monotone convergence theorem to show that the sequence converges. So in other words, that it has a finite limit. Okay, so it's like this is like part A, and this is like part B. So let me do part A first. Part A, an plus 1 divided by an equals, so an plus 1 is obtained from the formula for an by replacing n plus 1, n with n plus 1. So this is going to be n plus 1 factorial divided by n plus 1 raised to the power n. Divided by n by an, right? So, but to divide by a fraction, we need to multiply by the reciprocal of the fraction. So n to the n divided by n factorial. All right? So this is n plus 1 factorial divided by n factorial times, n plus 1 here. N raised to the power n divided by n plus 1 raised to the power n plus 1. All right, now let's look at this product. So n plus 1 factorial is the product of all numbers from 1 all the way until n plus 1. So in particular, it includes 1, 2, 3, 4, and so on up to n. And n factorial is the product of numbers from 1 to n. Right? So when you compute this, basically almost everything is going to cancel out because there's going to be 1 on top and 1 on bottom, 2 on top and 2 on bottom, and so on up to n. So the only remaining term is going to be n plus 1. Right? So this is going to be like n plus 1 times n raised to the power n divided by n plus 1 divided by raised to the power n plus 1. Okay, but then we can cancel this again. All right, so this is n raised to the power n divided by n plus 1 raised to the power n, and then we can just take out the power, and the remaining expression is n over n plus 1, and this is raised to the power n. All right, so it seems like part A is done. Now part B. Okay, so if this is the ratio of an plus 1 and an, so this part, then how is an plus 1 expressed in terms of an? Basically multiplying this with an, we're going to get, an plus 1 equals this times an. So why do we care how the next term is expressed via the previous term? Because if every time to get the next term we need to multiply the previous term with a number that is smaller than 1, then what we get is a smaller number, and our sequence is decreasing. If we multiply by a bigger number, right, so then whatever we have is growing and the sequence is increasing. Now this is clearly less than 1, right? N divided by n plus 1, so we have a number n, we're dividing it by something that is bigger, so we get something that is smaller than 1, and then we raise it to power n, so which means that we multiply n copies of number that is smaller than 1, and the result is still smaller than 1, because every time we multiply by a number that is smaller than 1, so what we get is something even smaller. Okay, so since every time we multiply with a number that is smaller than 1, our sequence is decreasing, strictly decreasing even. Okay, So one of the conditions of the monotone convergence theorem is checked. So to apply the theorem, we need to check that our sequence is either increasing or decreasing, and it happens to be decreasing. And besides, we need to check two more things. So we need to check that it is bounded. Well, our an is n factorial divided by n to the n. So n factorial is a positive number, n to the n is a positive number, so it is definitely positive. All right? So all the terms of our sequence are positive. On the other hand, our sequence is decreasing. So a1 is bigger than a2, a2 is bigger than a3, and so on. So all the terms of our sequence are definitely smaller than a1, right? So an is bigger than 0, and it is also smaller than or equal than a1, which is, I guess, just 1. So all the terms of our sequence are sandwiched between 0 and 1, and the sequence is decreasing. So it means that the monotone convergence theorem can be applied, and it tells us that the sequence converges.